This is a metal surface which can be electrified. We'll explain exactly what this means in a moment, and also how it's done. Right now, let's see what happens. I've got to operate the machine, but you watch the balloons. Here, obviously, is a force of some kind, and it's not gravity. We've never been able to turn gravity on and off. Nor is it magnetism. Whoever saw a magnet attracting something made of rubber? Yet it's an extremely important kind of force, for the pull which held these balloons together is in fact identical in character to the pulls which hold atoms together. For instance, it's the same pull which stops this drop of water from falling apart. It may seem a big step from the attraction this comb has for this paper to the strength in this enormous cable, or for the still greater strength, weight for weight, in this tiny thread of a spider. But it's this connection which is going to occupy us for much of the rest of the course. But electricity means not only force, it also means light. Indeed, electrified particles are the original cause not only of light, but of every form of radiant energy. Here's an example, but we'll need the lights off to see. Another case is the spark, and of course, lightning. This film is really about electrostatic charges. What types there are, how they behave, how they're produced, and so on. Now let's see if we can use these electrical forces to find out something more about charge. Now, here's a coat hanger made of plastic. I'm going to charge this by rubbing with a wool scarf. Friction's a very general method of giving materials an electric charge. Think of when you walk across a carpeted floor and get a shock when you touch the doorknob. Now I've suspended this, and I'm going to take another material. This time a brush made of a different plastic. And I'm going to charge this with a different material, a Dacron sock. Now, we find that the brush attracts the hanger. What about a comb? I charge it, and this time we get a repulsion, quite strong. Now this is something quite new. We've never met a repulsive force before, and it proves once again that it can't be anything to do with gravity. Gravity never repels. It also proves that there must be at least two ways in which a body may be charged. These two charges are called positive and negative. Now let's see what the reaction is between these. For this I'll have to suspend the brush, which is not quite so easy. There we are. Now, I'm recharging this because things don't hold their charge indefinitely. And this time, we get an attraction. Apparently, differently charged bodies attract each other. How about similarly charged? bodies? Well, we can find out this by taking an identical coat hanger, charging it, and the answer is they repel. This turns out to be a general rule. All sorts of materials can be given a static charge, sometimes positive, sometimes negative. But always, oppositely charged bodies attract, and similarly charged bodies repel. But what are these charges? What is their mechanism? Now, a warning. We haven't as yet given any evidence for this. But later in the course, we shall find that the mechanism's as follows. The two kinds of charge, which we've just discovered, are mirrored at the atomic level, where again, there are two kinds of minute charged particles, positive and negative. Now, in any ordinary chunk of stuff, this is meant to be a scarf, their numbers balance. Their charges cancel out, and the result is electrical neutrality. This is why neither comb nor scarf normally show any reaction. Now, the negative particles, or electrons, are fairly easily detached. According to this view, charging is the transfer of electrons from one body to another. We rob Peter to pay Paul. Here, the comb's receiving a surplus, and so becomes negative, whereas the wool is left with a deficit and is therefore positive. Now, the next thing to find out is whether these surplus electrons can move about or migrate within a charged body. Suppose we take a charged comb and touch this metal wire. If the surplus electrons are free to move along the wire, down this metal rod to those two leaves, both the leaves should receive a similar charge and so repel each other. Now watch. I'm charging the comb, and I touch the wire. The charge on the sphere is instantly shared with the leaves. All metals are good electrical conductors. Now here we have a string instead of the wire. And this time, we get no repulsion. Now suppose we wet the string. This, by the way, is why electrostatic experiments work better in dry weather. Now, we get a slow repulsion, because water helps to move charges about. The difference between insulators and conductors is only one of degree. For example, in this respect, the human body is about halfway between a good conductor and a good insulator. They're good enough conductors for us to be able to discharge objects by touching them. Here, the charge has leaked away through my body to earth. This is called grounding. Can charges be transferred from one body to another? Well, we've already assumed they can be by simple contact, as when we grounded the leaves. But here's a more ingenious demonstration. Now, we're going to give this plate a negative charge, which means that it'll always have a supply of surplus electrons. To do this, we use a machine similar to the one you saw at the beginning of the film. And this ping pong ball has been painted with aluminum to make it conducting. And when it hits the charge plate, it'll pick up some electrons, become similarly charged, and therefore be repelled. When it hits the uncharged plate, it'll give up some electrons, and so again be repelled. Therefore, the ball ought to bounce to and fro like a pendulum. Well, we switch on and start the ball. Now, why is the ball going slower? The machine's still going. Let's stop and think. Each time the ball hit this plate, it transferred some more electrons, so that the charge on the plate built up progressively. And this made it harder and harder for the ball to approach. If this explanation's right, we should be able to remove the charge on this plate by grounding, and so restore the situation we had at the beginning. Right? Ground it. Ground it again, and each time the ball goes faster. So much for transfer of charge by contact. And now, induction of charge. I'll have to give the hanger another rub. For this, we take an ordinary table knife, uncharged. I'm grounding it. Now watch. Now this really is extraordinary. This was an uncharged knife, and yet it must have become charged when it came near the hanger. But how? This isn't charging by contact. There is no contact. The explanation is that the surplus electrons on the hanger push the movable electrons along the conducting metal knife toward the handle, thus creating a shortage on the blade. This leaves the handle negative and the blade positive. But since the blade is nearer to the hanger than the handle, its attraction will overpower the handle's repulsion. Such a separation of charge is called induction. Now, this is not easy to demonstrate. We need a method of labeling charged surfaces, and since this particular method's rather messy, I put on a lab coat and gloves. Here is a yellow and a purple powder, and here is a mixture of the two. When shaken together, friction between the grains gives each powder an opposite charge. We'll check that the mixture works first using these two plates, both of which have also been given an opposite charge. Now, watch. The grains separate. The yellow go to the negative surface and the purple to the positive. Don't, of course, think that charges are colored. This is just a method of labeling them. Next, we'll use this globe to represent the table knife, because the shape of the table knife raises problems. We'll try and induce a charge on it using the usual generator. The generator will be negative, so the induced charges should be positive, purple, negative, yellow. Let's try. As predicted, positive negative. Now let's get all this mess cleared up and go back to the hangar. But charged bodies attract not only uncharged conductors, like the knife, but insulators too. Here's a glass bottle. Or a wooden-handled brush. Or a leather shoe. Now, in these cases, we know there cannot be no simple migration of electrons over the insulating surface. It must be that the negative part of each insulator molecule is pushed away slightly, and the positive part pulled nearer. Such a distortion is indetectably small in the case of a single molecule. But when totaled up over billions, it does result in a net separation of charge. Of course, this now comes as no surprise. Here's the machine for generating static charge, which we used at the very start. It's called a Van de Graaff, after its inventor. And we're now in a position to understand in principle how it works. Indeed, there's no reason why you shouldn't construct your own. Here's a junior model, which has the advantage that it can be taken apart. The Van de Graaff consists essentially of a hollow metal sphere, separated from the rest of the machine by an insulating column. The aim is to accumulate a charge in the form of surplus electrons on the sphere. And the electrons are carried to the sphere on an endless insulating belt, which travels between two pulleys, here and here, and is driven by a motor. The electrons are sprayed onto the lower end of the belt from the teeth of a charged metal comb. The comb is charged either by induction or from an outside source. The electrons are removed by a second comb. After being conducted to the sphere, they push each other away and so spread out all over its surface. And here is the biggest generator of this type ever built, now a museum piece. We ourselves are now inside the sphere, which is so large that it was originally designed as a small laboratory. In this machine, 3 belts are used. And here are the combs. Here's the machine in action. Don't think, however, that the scientific purpose of Van de Graaffs is to produce sparks. Many are used to produce X-rays. Other machines are used for atom smashing. This is the target area at the bottom of the world's most powerful Van de Graaff. Now we need a convenient and sensitive way of detecting charge. The powder method was altogether too clumsy. For this purpose, a good instrument is the electroscope. Its essential feature is a pair of metal leaves. Whenever this rod becomes charged, the leaves fly apart. Now I'm going to charge the electroscope by simple contact. More usually, charging is done by induction, and the steps involved in this will serve as a useful review. We saw that a charge body can induce a charge in nearby objects which were previously uncharged, both insulators, like the bottle, and conductors, like the rod and leaves. Charges can also be transferred by direct contact. A particular case is grounding. Here it's the negatives which are grounded, because the positives are still strongly attracted by the comb. Materials in which charges are free to migrate are called conductors. Those in which they are not free to migrate are called insulators. We can now use the charged electroscope, for instance, to detect the sign of unknown charges. But here's a different, interesting application of the instrument. If air were a perfect insulator, a charge, once placed on the leaf system, could never leak away. It would stay constant with time. In practice, depending on conditions, the leaves do slowly collapse. The rate of their collapse is, of course, a measure of the rate of charge leakage. Here they're collapsing faster. Things which are particularly effective in destroying the insulating properties of air are X-rays. Now watch, this happens quickly. Also, certain kinds of atomic radiation, such as that which is given off by this radium source. Now, this isn't the sort of thing you fool around with. An electroscope is, therefore, a means of detecting such agents, and in various forms is carried by thousands of workers in atomic industries to check their exposure to dangerous radiation. Finally, an intriguing problem. Even when an electroscope is carefully designed to prevent leakage of charge by conduction, and even if it's also shielded against external radiation, there is still a slight loss of charge. Strangely, this gets less if we go down into the earth, as in a coal mine. Conversely, the rate gets greater in the stratosphere. Why? Now go home and make your own electroscope. From a milk bottle, a nail and some metal leaf. And your own Van de Graaff, from anything you can find around the house. And try and explore some of these questions for yourselves.